All right, let's talk about something that can look, well, a little scary at first, the logarithm. But I promise you, by the end of this journey down the rabbit hole, you'll see it's actually one of the most elegant and honestly powerful ideas in all of math. So let's jump right in. Okay, I want you to imagine something. Picture a world with no calculators. None. How would you even begin to multiply huge, massive numbers together? It'd be a nightmare, right? Slow, tedious, and you're almost guaranteed to make a mistake. But what if there was a secret code? A trick to turn that awful multiplication into super simple addition? Well, that's exactly the puzzle we're going to solve today.
Here's our game plan. First, we're going to jump back in time to understand the puzzle that started it all. Then, we'll pull back the curtain on the logarithm's secret identity. And trust me, it is way simpler than you think. After we learn the rules of the game, we'll see how it all connects to stuff you already know. And finally, we'll go on a hunt to find where logs are hiding out in your world.
So, Section 1, a pre-calculator puzzle. Seriously, why did someone go to all the trouble of inventing these things in the first place?
You've got to remember, logarithms weren't just invented for a math class. They were created out of pure necessity. Back in the early 1600s, think about astronomers trying to map the stars, or sailors navigating the seas. Their calculations were massive. So a guy named John Napier came up with logs to speed everything up. Later, brilliant minds like Henry Briggs and the legendary Euler refined the idea, creating tools that would basically power science and engineering for centuries to come.
All right, let's get to the heart of it. If you only take away one thing from this explainer, please make it this next idea. Because once you see it, all the mystery around logarithms just disappears. And here it is, the big secret. A logarithm is just an exponent in disguise. That's it. It's not some new complicated operation. It's just a different way of asking a question about exponents. You're just looking at the same old puzzle from a brand new angle.
Now, this is so important. This is all about math literacy. Let's read it slowly, maybe even say it out loud with me. Log base b of x is the power you put on b to get x. Do you see that? The answer is literally written inside the question, if you just know how to read it.
Let's see this in action. We've got log base 10 of 1,000. So, using our new sentence, we read this as, what is the power I need to put on 10 to get 1,000? Well, let's think. 10 to the power of 1 is 10. 10 squared is 100. 10 cubed is 1,000. Boom! There it is. The power is 3. The answer was right there the whole time.
So now that we know logs are just exponents playing dress-up, it makes sense that the rules they follow are just the exponent rules you already know, just in a new outfit. And this is where their real power to simplify problems really comes from.
Here's the first magic trick, and it's the whole reason logs were invented. They turn hard multiplication into easy addition. Just think back to your exponent rules. When you multiply powers with the same base, you add the exponents. Well, since logs are the exponents, the log of a multiplication becomes the addition of the logs. It's that simple. And you probably guessed it, the exact same logic applies to division. The old rule says when you divide powers, you subtract the exponents. So it's no surprise that the logarithm of a fraction becomes a simple subtraction problem. It's all perfectly consistent.
And this last rule, this one's a real powerhouse. Remember that raising a power to another power means you multiply the exponents. This log rule mirrors that perfectly. It lets you take an exponent from inside the log and just bring it out front as a simple multiplier. This is an absolute game changer for solving complex equations. Okay, so we've been saying that logs are exponents, but what does that really look like? Let's visualize the relationship between an exponential function and its logarithmic buddy. And this graph illustrates it brilliantly. Just look, that steep upward curve is y equals 2 to the x. That's that explosive multiplicative growth. Now look at the slower, flatter curve. That's y equals log base 2 of x. They are perfect mirror images of each other, reflected across that central diagonal line. They're what we call inverse functions. One perfectly undoes the other.
All right, so this is all great math theory, but why should you care? Well, it turns out this so-called secret code isn't so secret after all. You've actually been using it, probably without even realizing it.
Out in the real world, you'll mainly run into two types of logs. On one hand, you have the common log, which uses base 10. This is incredibly useful because our entire number system is built around 10. On the other hand, you have the natural log, which uses a special, kind of magical number called e as its base. E is all about continuous growth, so you find the natural log everywhere, from calculating interest to modeling populations in biology. So where is this code hiding? Ever heard of the pH scale for acidity? That's a log scale. The decibels used to measure sound, log scale. The Richter scale for earthquakes, you guessed it. All of these things deal with a massive range of values. The difference in energy between a magnitude 4 and a magnitude 5 earthquake is huge. Logarithms compress these vast scales into simple, manageable numbers like 1, 2, and 3, making the world way easier to understand. That's their true power.
So the next time you see that log symbol, don't shrink away. Remember, it's not a monster. It's just a question in disguise, asking, hey, what's the power? So take a breath, take a look at the log, and just know that you've got this. Thanks for watching.